Thank you for joining us today. We are here to present our novel technology, Western Blot detection on a microplate meter. I am Brian Kloss, the Product Marketing Director at Melco Devices. We also have Vanitha Thulasiraman, a Senior Staff Scientist with Melco Devices, here to provide us the technical overview of our ScanLater Western Blot detection system. Earlier in 2013, Melco Devices introduced its SpectraMax i3 multi-mode plate reader to the market. It was our intent with the SpectraMax to not only provide the basic three-mode detection capability of luminescence, fluorescence, and absorbance, but to also provide scientists with the ability to expand beyond the classic microplate applications. In March, we introduced first-of-its-kind cellular imaging to the plate reader with our Minimax imaging cytometer, enabling scientists to do cell counting, proliferation assays, cytotoxicity assays, and much more. We recently added a user-installable cartridge for Western Blot detection called our ScanLater Western Blot detection system, which we are going to talk more about today. We believe the true benefit of having both plate reading capability and Western Blot detection on the same platform is the ability to compress your protein detection workflows to a single instrument. You can now perform both your downstream and upstream Western Blot assays, like ELISAs, Bradford assays, or protein quantitation via 280 nanometer absorbance on a single platform, which is supported by a single software analysis package. There are three components of a ScanLater detection system. The first is a user-installable cartridge, which installs in just minutes on either our SpectraMax i3 or our SpectraMax Paradigm multi-mode microplate platform. We also have three kits available, which include blocking buffer, wash buffer, and the europium-labeled antibodies, or streptavidin. We have the europium-labeled goat anti-rabbit, goat anti-mouse, and streptavidin. And each kit has been configured to provide enough reagents for 30 membranes. The final component is our image acquisition and analysis software, which is supported by SoftMax Pro, the same software used for setup analysis of the microplate-based assays. I'm going to introduce Vanitha Thulasiraman, who has more than 20 years of experience in proteomics. She is currently a senior scientist in the assay development group at Melco Devices, where she focuses on developing new assays in drug discovery and research. Vanitha was a lead scientist in developing the ScanLater Western Blot detection system, and prior to her work at Melco Devices, Vanitha spent much of her time in proteomics as a staff scientist at Biorad. Vanitha's thesis and postdoctoral research at Stanford University enabled her to acquire a broad expertise in Western blotting methods and has a valuable experience in the proteomics field.
Thank you, Brian, for the introduction. And today I will cover the assay principle followed by the detection method and how does ScanLater compare with the market benchmark chemiluminescence. What is the sensitivity and dynamic range of detection using the ScanLater Western? Importantly, how does ScanLater Western perform with real samples? Finally, wrapping it up with conclusion slide and opening it up to questions. And this slide shows the overview of the assay principle. As you can see, up till the step 5, the ScanLater Western is identical to Chemi. At step 6, instead of adding HRT-labeled secondary antibody, we would add europium-labeled secondary antibody. And as soon as we do the wash of the secondary antibody, the blots are ready to scan. And we can read the blot on existing plate reader. No substrates are required. And the secondary antibody is labeled with an europium chelate, and once again the blot can be scanned immediately after washing. And the next slide shows the workflow comparison of chemiluminescence, ScanLater TRF, and the fluorescence method of detection. As you can see, at the step 8 in chemiluminescence, you need to incubate with substrates for 5 minutes, and this step we can skip in ScanLater TRF and in fluorescence intensity. So there is, in ScanLater Western, once again, there is no need to add any substrate. no trip to the dark room or exposure to film, developing chemicals or films, no optimization of exposure time. In fact, the signal is stable for months, hence no need to scan immediately if the instrument is being used by another researcher. And to the next slide. How do we detect the signal? So we have special membrane holder, accommodates membrane up to 11 by 7 centimeter area, and it can hold smaller membranes. And we can read it just like you would read any other microplate. And how do we detect? We detect by PMT, the photomultiplier tube. So it takes up to 5,730 measurements per square inch, thus giving high sensitivity and large reading range. And it results in a 16-bit image, which means we can see up to 4 logs of detection. And moving to the next slide. So what makes europium unique? It has long fluorescence time of about 1 millisecond. That allows us to pause before we acquire the emission. We have a lag of 200 nanoseconds before we start collecting the emission signal. And that's what significantly reduces the autofluorescence of short lifetime emissions, and thus increasing the sensitivity of the ScanLater Western. Additionally, europium has a large Stokes shift. We have a large Stokes shift in between the excitation maximum and emission maximum at 617 nanometer. This again reduces the autofluorescence background from short emissions, from short lifetime emissions. And moving to the next slide. How does the ScanLater Western compare with the market benchmark chemiluminescence? So here in this study, we compared the sensitivity of ScanLater TRF based Western with the chemiluminescence based Western. So the first thing that we wanted to do was, how does ScanLater Western compare to the market benchmark chemiluminescence? The question that we wanted to address was, how do we compare sensitivity of ScanLater TRF Western blot to chemiluminescence based Western blot? And how did we do this? We took extracts of HEK293 T cells treated with different levels of carcinogen, MMS, and they were run on a gel and transferred to immobilon F and probed the primary antibody and then the europium labeled anti-mouse antibody, or else it was labeled, it was exposed to HRP labeled anti-mouse antibody from Millipore. And finally, it was quantitated using image J, and you will see the results. ScanLater is as sensitive as chemiluminescence, and it is more precise and quantitative than chemiluminescence. So the slide here on the left side is the result from the ScanLater Western. The 0 represents no exposure. The next one is 50 parts per million of MMS and 100 parts per million of MMS. You can see 2 bands. The top band represents the ubiquitinated RAD18, which is targeted for proteasome-dependent degradation, and the bottom band is the unmodified RAD18. So we can see that with increasing amount of MMS, there is decrease in the amount of ubiquitinated RAD18 and increase in the amount of unmodified RAD18. And you can clearly see that the ScanLater TRF Western is comparable and as sensitive as chemiluminescent Western. So this slide, I forgot to mention, the data was generated in collaboration with Stanford University, and it was presented in a poster poster in Basel, Switzerland. Here this model was taken from molecular cell published by Simpress Lab in Stanford University. When there is no damage, RAD18 is in complex with HLTF and SHPRH. But when exposed to MMS, HLTF is polyubiquitinated, targeted for proteasome-dependent degradation. And RAD18 in complex with SHPRH, factor X, and polymerase K prevents mutagenesis. So this you can clearly see in the next slide where we have quantitated the signal of RAD18, both the unmodified and the modified form. So the bar graph on the left shows how well the unmodified RAD18 increases with increasing amount of MMS, and the modified RAD18 decreases with increasing amount of MMS. So this clearly captures what is actually happening. But then if you look at the quantitation aspect in the right side bar graph, you can see the increase in the unmodified, but then in 100 parts per million it comes down. And so we all know already chemistry is a little weak in the quantitative aspect, and this is overcome using the ScanLater TRF. Once again, ScanLater TRF Western is more quantitative and precise than chemiluminescence Western. So how sensitive and what is the dynamic range of the ScanLater TRF? This we have addressed by looking at the GST detection, where we do 3-4 dilution series of GST in 1x sample buffer and loaded on a 4 to 20% gradient gel. After the gel was run, the proteins were transferred to immobilon FL membrane and probed with biotin-labeled rabbit anti-GST, followed by incubation with europium-labeled streptavidin. The blots were washed, dried, and scanned using SpectraMax reader. You will see the results. The system has demonstrated sub-picogram detection limit of GST with over 4 logs of positive response of signal versus amount of GST. Images were created using SoftMax Pro software version 6.3.1. On the next slide, you can clearly see that you can detect from 7,000 picogram to 0.1 picogram of GST with no saturation. That is clearly more than 4 logs of positive response of signal versus the amount of GST. So the beauty of this is from the SoftMax Pro, we can export the raw PMT to Excel without any manipulation. And in the Excel, using the Excel algorithm, the bands are automatically segmented and quantitated. Extends the dynamic range beyond the 16-bit image. On plotting the raw PMT versus the amount of GST, we can clearly see a linear response with R-square value greater than 0.996. And this is very impressive for me when compared to the chemi. And with that, the next question that came to our mind is, how stable is this signal? Is it stable for a month? And can we acquire data multiple times without losing any signal? So we wanted to answer the 2 questions. For this, we loaded 2-4 serial dilution of transferrin, run on a 4 to 20% gradient gel, transferred to immobilon FL, and the blots were washed, dried, and scanned using SpectraMax reader. The membranes were scanned on day 1 and day 30, and then the membranes were scanned several times. And you will see that europium signal is stable for over a month time frame, and results are highly reproducible without signal loss. Going to the next slide, you can see that the results from day 1 on the left side and the results from day 30, they are very identical. As you can see from the graph, the quantitation of each band overlays for day 1 and day 30. So again, showing that europium signal is stable. And the next slide shows where I have done multiple scan of the same blot. The blot on the left shows the first scan, and the blot on the right shows the 7th scan. And in this case, we quantitated the 5th band, which corresponds to 250 picograms of transferrin, and the bar graph below shows the results over the 7 scans, and you can clearly see they are very similar. And I would like to point out this was done using image J, where the bands are not automatically picked. So there is some variation when you try to manually pick the bands. So some of the variation that you see in the quantitation is because of the manual band picking. And this is very impressive, that clearly there is no loss of signal, so you can scan the same blot many times. And you can even come after a month if you want to look at other part of the blot, you can rescan the membrane. So that's the added advantage of using ScanLater Western. So now coming to the exciting part, how does the ScanLater perform with real samples? I'll be showing you a few examples. The first one is, can we detect endogenous levels of phosphorylated NF-kappa B in mammalian cells? So in this case, we took human skeletal muscle cells that were treated with TNF-alpha for 24 hours, and then they were run on a 4 to 20% gradient gel, blotted to nitrocellulose membranes using the transblot turbo, blocked for an hour, and incubated overnight with the primary antibody, followed by incubation with secondary antibody. The blots were dried before scanning using the SpectraMax multimode reader. And you will see in the result that we could detect both total and phosphorylated NF-kappa B in HSK-MC cells. So the next slide shows. Here on the left side, the blot shows a signal from total NF-kappa B. The first or every alternate is control cell lysate, and the other lanes are TNF-alpha treated cell extracts. If you look at and then we have the bar graph right below, and here we have loaded different amount of total extracts. One is 20 microgram, 10 microgram, and 5 microgram. So if you look at the total NF-kappa B, there is not much difference in the expression when you compare TNF-alpha with control. But then if you see the blot on the right, which represents signal from phospho NF-kappa B, you can clearly see upregulation of the phosphorylated NF-kappa B when the cells are treated with TNF-alpha. And you can consistently see that in 20 microgram, 10, and 5 microgram. So we could capture the difference in phosphorylation expression using the ScanLater Western. And the next example is, again, how do we detect two proteins in the same blot? In this case, we took HEK293 protein homogenase in a concentration range of 100 to 0.1 microgram, and they were separated via electrophoresis and scanned and developed using the ScanLater Western Blot protocol. And we successfully could detect both housekeeping protein beta-actin and EIF2 alpha. And that's what the next slide would show, where we could clearly see the top band represents the actin and the bottom represents the EIF2 alpha, where we could successfully detect both proteins in the same blot. And moving to the next. Again, here we looked at endogenous kinase in mammalian cells. In this case, we used natural human lung fibroblast cells, which were treated with stimulants and inhibitory drugs, and then they ran on a 8% plus glycine gel and transferred to immobilon P, blocked in 5% milk, and primary antibody was added overnight. After wash, europium-labeled anti-mouse antibody was used and washed and scanned using SpectraMax reader. And the result, you will see that we could detect trace amounts of endogenous GNK in NHLS cells. And that's what you will see in the next slide. The first lane represents a cell extract that was not stimulated, and the next one represents extract from the cell that was stimulated and no inhibitor added. And if you see the bar graph below, you can clearly see a clear upregulation of phosphorylated GNK. And the next lane represents extracts from cells that were treated with the highest level of inhibitor at 10 micromolar in the presence of stimulant. and you can see clear down regulation of GMK. And as we decrease the level of inhibitor, the level of phosphorylation comes up. And this will be the last application where we wanted to detect phosphorylated PCHK1 in mammalian cells. Once again, we used HEK293 cells treated with either carcinogen MMS or exposed to UV radiation and run on a 4 to 20% gradient gel. Transfer to immobilon FL and probe with primary and secondary antibody and read on a SpectraMax reader. You can clearly detect very low amounts of endogenous phosphorylated form of PCHK1 in HEK293 cells. You'll see that in the next slide. In control cells, the level of phosphorylated CHK1 is very low, but when you expose it to the carcinogen MMS and UV radiation, you can clearly see the upregulation of the phosphorylated form. And upregulated PCHK1 is a potential marker for persistent DNA damage, and you can clearly capture that using a ScanLater Western. And coming to the final conclusion, you could clearly see ScanLater Western is very sensitive. We could detect very low amounts of endogenous phosphorylated and ubiquitinated proteins in human cells. And we could see the reduced background mainly because of the europium has long fluorescence lifetime and has large Stokes shift. And we could directly quantitate. The raw data can be exported to Excel with automated band picking. And we save time, no time-consuming ECL optimization is required. We reduce costs because we eliminate the need for laborious and expensive X-ray films and developer. And it's ready to go. Works with existing SpectraMax paradigm and SpectraMax i3 instrument. And with that, I'll open it up to questions. Oh yeah, I would also like to add the final slide where I would like to acknowledge Simprish Lab in Stanford University, Jaron Lin, and also we worked in collaboration with Novartis in Basel, Switzerland, Jacob and Simone, and in molecular devices we have all of us, as shown here, have helped in making the product available to all of you. And with that, I'll open it up for questions.
All right, the first question that we have from the panel is they want to know what membranes are compatible with the ScanLater Western Blot system.
They would recommend immobilon FL, but as you saw in some of the slides, we use immobilon T, nitrocellulose membranes, so other membranes are also compatible. For best results, use immobilon FL.
Another question came in is whether or not I can use my own wash or blocking buffers.
The wash buffer and block buffers in the kit are optimized for best performance. But if you have your own buffer and wash and blocking buffer that you have optimized for your assay, I would recommend using your own. But if you have problems with that, definitely use our kit. It is optimized for the Western blot application. Yes.
Another question that was written in, is it possible to automate the Western blot solution? And the answer to that question is yes. If you saw earlier, the membrane holder, which holds the Western blot membrane, it conforms to the SBS plate standard, so that would work with any of your existing automation systems. Another question that came in is it possible to scan the membranes wet or dry?
We can scan the membrane both wet and dry. When you dry the membrane, the signal-to-noise ratio is higher, but you can definitely see your results when the blot is wet.
That was all the questions that came in. We'd like to thank you for attending the ScanLater Western Blot webinar today. We'll be sending the recording out to those of you that were not able to make it, and those of you that would want to go ahead and view it again. In that email that we sent out, we'll also have an offer for you to try the ScanLater Western Blot membrane system in your lab. So if you're interested, go ahead and reply to the email, and we'll go ahead and send you out samples. Thank you very much for your time today.